So we are in section 3.3. Here we are solving systems of linear equations using a method called substitution. So in the last section, 3.2, we talked about how to solve these systems using graphing. So if I were to go ahead and graph these two linear equations, which I already did on Desmos, we would graph these two lines and we would see that they intersect at 1, -1. So we know that our answer should be x equals 1 and y equals -1. They do intersect. So if we go back to this one, what we're going to do is we're going to use this substitution method. Now how substitution works is we know that the value y is the exact same thing as 3x minus 4, right? I can think if I had like a scale, right? On this side we had the letter y, and on this side we've got 3x minus 4. They're balanced, right? They weigh the exact same amount, right? Even though they look different, they're the same thing. So what I know is, let me erase this. Okay, if this y is equal to 3x minus 4, then this y over here must also be equal to 3x minus 4. So what we can do is we can substitute this y with the 3x minus 4. So what I can do is, replacing this y, I'm going to replace this with the 3x minus 4, and that's got to equal negative 2x plus 1. Okay, so I'm just changing out this y for that 3x minus 4 because that's what y equals. So now we can go ahead and solve this. If I add 2x on both sides, we end up with 5x. I'm also going to add 4 on both sides to get the constants on the same side. So 5x equals 5, and then we divide by 5 and we figure out x is equal to 1. Okay, now I know what x is, which should make sense because we already know it should be 1 there. But I'm going to now take 1 and I'm going to plug it back into either of these two equations. So you can plug it into the top one or the bottom one. You're going to get the same answer either way. I'm just going to choose the top one here, y equals 3x minus 4. And if I replace this x with a 1, we get y equals 3 minus 4, which is just -1. And again, that's what we would expect to get. So what that means is that my final answer is going to be 1, -1. This is where these two lines intersect. All right, so substitution works great when you have a variable all by itself, when it is isolated. All right, you have to have an isolated variable if you're going to use that substitution method. All right, now we're going to do another one. We're going to graph these two lines here, and we see that these two lines intersect at 4, 3. Now neither of them are in slope-intercept form, and the first one's not even in standard form either. So we're going to have to, again, try to isolate either x or y, and then we're going to substitute it into the other equation. All right, so if we go down here to the second problem, again, we see the answer should be 4, 3. So I'm going to try to get a variable by itself. And the nice thing about this is you get to pick which one you want to get by itself. So if I look at the y, the x, this x, and that y, I believe that this x is going to be the easiest to isolate. All right, that's just personal preference. I think it's going to be the easiest. All I would have to do is subtract 5 on both sides of this first equation, right? And if I do that, we're going to end up with a new equation, and that's going to be x equals 3y minus 5. All right, so we just rearrange this first equation, right? We want to isolate the letter x in this case. And now I know that x equals 3y minus 5. So in the other equation, I can substitute it for that letter x, right? We know x is the same thing as 3y minus 5, so we can just use that substitution. So now, taking this new equation, we've got 4. We're replacing the x with 3y minus 5. All right, and make sure you use parentheses when you plug it in. And then we have a minus y equals 13. All right, we will have to distribute this 4 to both pieces here. So now we've got 12y minus 20 minus y equals 13. If I subtract, combine my like terms here, 12y minus 1y is going to be 11y. And if we add 20 on both sides, we should see that that equals 33. Last thing we do is we divide by 3, and we end up with y equals 3. And again, that should make sense because we just saw that they intersect where the y value is 3. So now I can plug it into either equation, right? I know that y is 3, so we can plug that back in. I think the top one looks a little bit easier, you know, smaller numbers, so I'm going to plug it in there. X plus 5 equals 3y, but I'm replacing the y with a 3, we said. So now we get x plus 5 equals 9, and when I subtract 5, we get x equals 4, which again checks out. All right, so we do get 4, 3 as our final answer. And then the last one, this one, we see that they intersect at 1.5, comma 1.5. So if we look at the graph here, I graphed both these lines, and if we look, we do see that they intersect at 1.5, comma 1.5. Now, some of these are not necessarily super easy to do with this substitution method, right? If I look at these x's and y's everywhere, you're going to notice that none of them are by themselves, right? They're not isolated, and they all have a coefficient bigger than 1 in front of them. So I'm going to have to do a little bit of work to try to isolate one of these variables. But again, you get to choose whichever one you want, whichever one you think is going to be easiest. So I don't think this 6x is the one I want to get by itself, because if I divide by 6, that would give me some fractions. Same thing with this negative 2x. If I divide by negative 2, I'm going to get a 3 over negative 2, which again is a fraction, so I don't want to do that one. I don't want to divide by 4, because again we're going to get fractions, right, if I divide by 4. So I think the best one here is to try to get this negative 2y by itself, because if I divide everything by negative 2y, we won't end up with any fractions. So I'm going to rearrange this. I'm going to subtract the 6x on both sides, so negative 2y equals negative 6x plus 6. Then I'm going to go ahead and divide everything by negative 2, so we get 3x minus 3. And now I know that y is equal to 3x minus 3. So I can take this 3x minus 3 and I can substitute it in for that letter y. So rewriting my second equation, we get negative 2x plus 4 times 3x minus 3 equals 3. I then will have to distribute this 4, so negative 2x plus 12x minus 12 equals 3. When I combine my like terms, we get 10x, and then I add the 12 equals 15. And when we divide both sides by 10, we do get x equals 15 over 10, which does reduce to be 3/2, or 1.5. Okay, so again, that does check out for our x value. We get 1.5, which is great. And now I can plug in this 1.5 into either of these two equations, right? Doesn't matter, doesn't make a difference. Let's just try the bottom one, how about? So I'm going to take my negative 2x, but again, we said that x is now 1.5, plus 4y equals 3. I'm going to multiply this, so negative 2 times 1.5 is negative 3, plus 4y equals 3. I'm going to add this 3 on both sides. That's going to give me 4y equals 6. And when I divide both sides by 4, we get y equals 6/4, which reduces to be 3/2, or again, 1.5. Okay, and that does make sense. We would expect the y value to be 1.5 as well. All right, so the main thing when you're doing the substitution method is to isolate either the x or the y, whichever you think will be easier, right? Try to avoid any fractions. Obviously, some of these will already be set up for you nicely, right? Like this very first one, we already had y isolated, so we just plugged it in. For problem number 2, we had to do a little bit of work, right? We had to move the 5 over by subtracting, and then we got x by itself, and we could substitute. And then this third one, we had a little bit more work to do. We had to do a little bit more solving and isolating, but once we got y by itself, we plugged it in, and we solved. All right. The nice thing about these is you can always check your answers by plugging them back in. You can also verify your answer on Desmos, because if you graph these and they intersect at your answer, then you know you've done the problem correctly.